The last section, or last part of section 2.6, deals with transformations of linear functions. Specifically, we're going to talk today about vertical stretch and compression. Very simply, if you want to stretch or compress a function, that means it grows by a factor of some number, grows or shrinks. And as I'm writing at the bottom, you take your original function f of x and you multiply the entire function by some value a. Whatever a is, you take the entire function and you multiply the entire function by whatever a is, and that is how you get it to stretch or compress. Now, a vertical stretch means that the graph moves closer to the y-axis. Now, as far as a line is concerned, that means the line gets steeper. As far as a vertical compression is concerned, that means the graph moves closer to the x-axis, and that means the line is less steep. So I'm going to write that over here. Vertical stretch, the line is steeper, and vertical compression, the line is flatter. Now, how do you achieve that? It all deals with what number a is. If the absolute value of a is greater than 1, meaning if you have a number that's bigger than 1, it will be a vertical stretch. If you have the absolute value of a is a decimal or a fraction between 0 and 1, then it is a vertical compression. And that is the whole distinguishing factor as to whether it's a stretch or compress. If you need to pause the video, please pause it right now, and then I will go on to some examples. All right, hopefully you wrote those notes down. Now, let's take a look at how this works. First of all, I want to graph the equation y equals x plus 2. Very simply, we all know the y-intercept is equal to 2, and the slope is equal to 1. So I'm going to put a dot at 2 for my y-intercept, and I'm going to go up 1 and over 1. I'm going to put another dot, and I'm going to go up 1 and over 1 and put another dot, and there is the graph of this particular linear function. Now, I want to graph the vertical compression of that function by a factor of a half. Now, how do you do that? Well, you take the function f of x, which is equal to x plus 2, and you multiply the entire function by the a value, which is a half. So that means I got to distribute this. So that means my function, which I'm going to call f prime of x, or my transform function, is equal to half x plus 1. Now, I'm going to graph that in blue. We know that the y-intercept is equal to 1, and our slope is equal to a half. So if I put a dot at 1, and then I'm going to rise 1 and go over 2 and put a dot. And I'm going to rise 1 and go over 2 and put a dot. And if you notice now, our line, and I'm going to extend this out a little bit. I'm going to extend both lines out a little bit. If you notice our line, our original line, which is in red, has now moved closer to the x-axis because it is being compressed. And a compression means, by definition, that it gets flatter. And that is how you can tell the difference between a stretch and a compression, and that's how you do it graphically. If you need to pause the video, copy that down, please go ahead and I'll do one more example for you. All right, last example. Let's do this mathematically. I have the original function g of x. It's equal to x plus 3. I want to know what is the new function h of x if g of x is shifted left 5 units, then stretched vertically by a factor of 4. In order to do this mathematically, we take our original function g of x and we write it down. The first thing it says, shift it left 5 units. From a prior video, prior lesson, we learned that in order to shift something to the left, you take the X and put it in parentheses, and left means that you add 5 to it. Addition means the opposite of what you think. Addition shifts the graph to the left. So now our function, after the first transformation, we combine our like terms and it becomes x plus 8. That will shift our graph to the left 5 units. Now, step number 2. It says stretch vertically, stretch by a factor of 4. Well, and our new function is going to be called h of x. So h of x is going to be our old function, which is x plus 8, and I'm going to multiply the entire equation by 4 to stretch it vertically. I need to distribute, and I get h of x is equal to 4x plus 32, which will be our transform function. So, starting with x plus 3, by transforming the original function x plus 3 left 5 units and then stretched by a factor of 4, I end up with this graph and this equation, which is quite a bit different. And that's how you transform functions mathematically. If you have further questions regarding this, please ask during class. But otherwise, that wraps up section 2.6.